A number line is helpful if we need to locate just a single point or a range of values. So number line is useful for locating a single number or a range. Right? So if we had something like this, we could locate if 0 is here, we knew that 2 would then be over here, or if we had less than -1, it's over here, right? So if x equals 2, we have just this point, or x is less than -1, we have that part over there. But what if we need to locate pairs of numbers? So imagine that we start with our number line. Looks like this, right? And our positive is over here, and our negative is over here. And we can place our 0 right there. Well, if I were to take a second copy of this number line, and I'm going to rotate it and put it here. When we rotate it, the positive comes up here, and the negative comes over here. This is called the coordinate plane. The coordinate plane is just two number lines that are perpendicular to each other. So perpendicular, if we had a geometry class, we put this little square bracket, which means that they're perpendicular. And we have some names for these things. This first number line we call the x-axis. And our second number line we call the y-axis. So our horizontal number line is our x-axis, and our vertical number line is our y-axis. So this coordinate plane helps us locate pairs of numbers. And pairs of numbers are called ordered pairs. And the reason we use ordered pairs is because suppose I have a coordinate plane, and I say plot the pair of numbers 1, 2. Well, how do I know if that's over 1, up 2, or up 1, over 2? So which one? So mathematicians have agreed upon a convention. And that convention is, in an ordered pair, the first value is the x-coordinate, and the second value is the y-coordinate. So 1, 2, hoping you can't see that. So 1, 2 is our x coordinate, and 2 is our y coordinate. Which means if I draw another set of axes, and if you want, you can write your x and y, just so I know which way it's oriented. And our x coordinate is 1, so on our x number line we find the 1, and our y coordinate is our vertical, so we have 1, 2. We know that this point corresponds to 1, 2, because we have the x and y. And so by convention, that first term, and that's why it's called an ordered pair, because we have an agreed upon order of these terms. We always put the x-coordinate first, and we always put the y-coordinate first. And I want to point out that when we're looking at an ordered pair, this looks kind of similar to if we had, say, up here on our number line, -1, 2, right? If we wanted to mark this point between -1 and 2, if we wanted to denote that range, we would write it that way. So it's important that we know whether we're talking about an inequality or we're talking about an ordered pair. And so to keep things simple, when we're talking about ordered pairs, we're only going to be talking about ordered pairs. And we won't be moving back and forth because it has the same notation. So let's talk about maybe plotting some of these points. So I'm going to give you a decently large coordinate plane. X, Y, I always put those arrows because they don't end at any of those points. And we have some examples. So I'm just going to write them all here, plotting the point 2, 2, -1, 0, 3, 0, 0, 4, -3, 1, 0, 0, -4, -1, and 0, -1. Now you might pause and kind of practice plotting each of those points, but then we'll go through them in turn, remembering that our first term is our x-coordinate and our second is our y. So x2, y2 is 1, 2, 1, 2. That's my point, 2, 2. -1, 0. X is -1. Y is 0. -1, 0. 3, 0. 1, 2, 3 on the X, 0 on the Y. 3, 0. X equals 0, Y equals 4. 0, 1, 2, 3, 4. Here we have 0, 4. -3, 1. X is -3. Y is 1. -3, 1. And then we have 0, 0. So that's this point where the two axes meet. And now this point in the middle has a special term, or a special name. 0, 0 is the origin. So wherever that point is, where the two number lines meet, where both x and y are 0, we call that the origin. -4, 0. X is -4. 1, 2, 3, 4. Oh, and it's -4, -1. So here we have -4, -1, and then 0, -1. And so there we were able to plot those points. And so based on that, we noticed some things. Whenever we're on the y-axis, here x was 0, and here x was 0. So x is equal to 0 whenever we're on the y-axis. And if we're on the x-axis, we had 3, 0, and -1, 0. Our y-coordinate will always be 0. If we're up here, our x is going to be positive, and our y will also be positive. If we're over here, our x is negative, but our y is still positive. So we have negative, positive. Down here, we have x is negative, and y is negative, so negative, negative. And down here, we have positive, negative, positive, negative. And so the coordinate plane, it kind of intuitively or naturally is broken down into these 4 pieces. And this is called the quadrant 1, first quadrant, which generally speaking I'll write as Q1. Here we have Q2, or the second quadrant, Q3, or the third quadrant, and over here we have Q4, or the fourth quadrant. And again, you're like, well, why did I go 1, 2, 3, 4? Convention is that we number our quadrants counterclockwise or anti-clockwise. So there's no reason that it couldn't have gone 1, 2, 3, 4, other than it doesn't. And by convention, mathematicians call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And so if we look at the quadrant, sine of x and sine of y, we have 1, 2, 3, 4. In our first quadrant, x is positive and y is positive. In our second quadrant, x is negative and y is positive. Our third quadrant, they're both negative. And in our last quadrant, we have positive, negative. And so those are properties that are always true. When we're plotting them, we end up with our positive and negative values. Jasper wants to join in on the math. Clear him a space. And so we have our 4 quadrants numbered counterclockwise starting at the x-axis. Quadrant 1, where they're both positive. Quadrant 2, where our x is negative but our y is positive. Quadrant 3, where both x and y are negative. And quadrant 4, where x is positive and y is negative. And so that's just kind of basic like orientation to the coordinate plane. And you can remember that these are quadrants because quad means 4, like a quadrilateral has 4 sides. But let's talk about distance. If I have a number line between these 2 points, say -1 and 4, the distance is just my right term minus my left, right? So the number of units between them is 4 minus -1, or 5. There are 5 units between these two. But if we're in a coordinate plane, is distance as straightforward? So let me draw, and I'm going to draw kind of an abbreviated coordinate plane. And I say, what's the distance between one, 1, and 4, 3? Well, first we'll plot it. So we have x and y, 1, 1, and 4, 3, 1, 2, 3, 4, 1, 2, 3. So that's my points 4, 4, 1, 3. And we want to know that distance. What is that distance? Well, I mean, if we looked at just this distance, we know that that's 3, right? Because from 4 to 1 is 3 units. Or if we look at the vertical distance, we have 1 up to 3, which is 2 units. So how do we find that diagonal distance? And this is where I'm going to remind you of something you may have heard once upon a time, the Pythagorean theorem. Pythagorean theorem. if A and B are side lengths and C is the length of the hypotenuse, of a right triangle, then A squared plus B squared equals C squared. So, since our x is always our horizontal distance and y is always vertical, and we already decided that those two axes were perpendicular by their definition, this vertical distance and this horizontal distance are perpendicular to each other. And that means we can use the Pythagorean theorem to find the length of this diagonal. So like I said, up here we can call this horizontal distance of 3 our A, and our vertical distance of 2 we can call B. So what we have is 3 squared plus 2 squared equals that unknown length C squared. So 3 squared is 9, 2 squared is 4, C squared. 9 plus 4 is 13 equals C squared. And that means that C is plus or minus the square root of 13. So remember, when we take our square root, we get a plus or a minus. But it doesn't really make sense to say that something is a negative length from somewhere else. And so by convention, we'll only use the positive distance. So the distance between this point and this point is the square root of 13, and we'll only care about the square root. So whenever you're finding the distance between 2 points, you plot them, you find their x distance, their y distance, and then we use the Pythagorean theorem to find the distance between them. Now what if I want to know, just like generally, between any 2 points? Suppose I have a point, x1, y1, and x2, y2. So that's just our first point's x value and our first point y value, second point x, and second point y. So wherever they are, x1, y1, and x2, y2, we know that that horizontal distance is x2 minus x1, and we know that that vertical distance is y2 minus y1. And so by our Pythagorean theorem, we know that x2 minus x1 squared plus y2 minus y1 squared is that length we care about. We'll call it L squared. And we can take our square root, and we get x2 minus x1 squared plus y2 minus y1 squared. And this equation, because it has an equal sign, is called the distance formula. Because for any point, x1, y1, and x2, y2, so any 2 points, the distance between them is given by this. You might say, well, how do you know which one's x2 and which one is x1? Well, it doesn't matter. As long as, if you have, say, and we can look at our previous example, we had the points 1, 1 and 4, 3. So call this x1, y1, x2, y2. What we end up getting as L is the square root of 4 minus 1 squared plus 3 minus 1 squared. But what if instead you were like, well, I'm going to call 1, 1, x2, y2, and I'm going to call 4, 3, x1, y1. Well, here what we get is the square root of 1 minus 4 squared plus 1 minus 3. And so let's simplify each of these. So here we get the square root of 4 minus 1 is 3 squared, plus 3 minus 1 is 2 squared, 9 plus 4, square root of 13. So it still works. But if we do this one with the square root of 1 minus 4, which is negative 3 squared, plus 1 minus 3 is negative 2 squared. Negative 3 squared is 9, plus negative 2 squared is 4. We still get the square root of 13. So it doesn't, sorry, there was a moth that just flew by, and it totally caught me off guard. Sure, that's a beautiful look of sheer terror on my face. Our length is the square root of 13. So it doesn't matter which point is point 1 and which one is point 2, as long as x1 and y1 are the same point, and x2 and y2 are from the same point. I can't say do x1, y2, x2, y1. Like I can't switch what they're partnered with. x1 and y1 just means both x and y values are from the same point, and x2, y2, both values are from the other point. But which one doesn't matter. 3 linear equations. And now we already started to look at some of these, particularly when we were graphing and when we were introducing functions and things like that in a previous video. So what we're going to do today when we look at linear equations specifically is we're really going to dig into some of the features of linear equations, some of the properties or characteristics, and then really digging into their graphs. So really focusing on this notion of graphs of equations, and that being the plotting of all the points that are solutions, right? Those values that make it true. And so I'm going to go to an image next, but I want you to have 2 questions in mind. What do you notice and what do you wonder? And after I show it, you might consider pausing it and really looking in and seeing, do you notice any patterns? Do you notice anything, any kind of associations? And maybe what kind of things do you wonder? And so here's that image. And now all of these are of the form y equals m times x. So we have y equals 3x, 2x, x, which is the same as 1x, 1/2 x, and 1/3 x. Here we have y equals 0, or 0x. And then we have a negative 1/3 x, negative 1/2 x, negative 1x, negative 2x, negative 3x. And then our y-axis here is x equals 0. So maybe pause here and take a minute just to look and see if you notice any patterns. Okay, so the first thing I want to point out is all of these lines in blue have a positive number in front of our x, whether it's 1/3, 1/2, 1, 2, or 3. All of those have a positive number in front of x. Now m, this is the coefficient of x, is called the slope. And I'll give you a formal definition of slope in just a little bit. But this number in front, this 3, 2, 1, 1/2, and 1/3, is slope. And all of these blue ones, as we go from left to right along the line, they rise, right? So they rise, they go up as we move left to right. Some of them rise faster, and some of them rise slower, but all of them from left to right, they rise. So left to right, a positive slope line rises. And then if we contrast that here with our red ones, from left to right, no longer are they increasing, but they're decreasing. So we say they fall. So left to right, negative slope lines fall. So positive rise, negative fall. Our horizontal lines, for example, y equals 0, and we could draw another one that say y equals 6, would move left to right. And so horizontal lines have slope equal to 0. And then for vertical lines, that's like our y-axis here. Notice they don't have an m at all. Here we just have x equals 0, so there's no y term. Or over here we would have x equals 6 being a vertical line, because that's all the points where its x coordinate is 0, because the origin is 0, 0. Or over here where all of their x coordinate is 6, right, would be a vertical line there. So for vertical lines, slope is undefined. So let's be a little bit more formal about slope. So we'll define slope as the steepness between 2 points. And now let's say those points are x1, y1, and x2, y2. So slope we say is the rise over the run. That's the change in y over our change in x. And now just for notation, the capital letter delta, the Greek letter delta, stands for change, so change in y over change in x. And we can calculate that by doing the second y value minus the first y value over the second x value minus the first x value. Now let's put that into practice. And I'll draw a picture to help us kind of see that. So let's say find slope between 0, 4 and 2, 0. And so if we would draw that, x equals 0, y equals 4. That's our point 0, 4. And 2, 0 is here. And so the line we're looking at is there. And so thinking already, based on our pattern we noticed here, left to right, it's falling, so it should be negative. So slope should be, and we'll just put that in parentheses, negative. And that'll be some way for us to check our work when we get to the answer. So our formula up here says our slope is our rise over our run. Our change in y over change in x, or y2 minus y1 over x2 minus x1. So let's go ahead and just give these names. I'll call this x1, y1, x2, y2, just to help us keep that in order So our slope is change in y over change in x. y2 minus y1 over x2 minus x1. y2 I said was 0 minus y1 is 4 over x2 is 2, x1 is 0. 0 minus 4 is negative 4 over 2, negative 2. And you're like, well, how can I see that in this graph? Now let me find my other pens, which I think are behind my laptop. They are not. Oh, they're over here next to me. If I remember when we talked about the distance formula, we drew our triangle in, and we said, well, this change is going to be y2 minus y1. And this one here is going to be x2 minus x1, right? It was that distance between our x coordinates and our y coordinates. And so because we do the vertical distance over the horizontal distance, rise is our vertical distance or change, and run is our horizontal distance. Right? And so this is where this notion of rise over run comes from. And what this tells us is for every units we go down 2, we go right 1. So that means if we go down 2, right 1, down 2, right 1, right? Notice how all 3 of those points then fall on that line. So when we were plotting points to graph our equations, we just found a bunch of points, put them on there, and connected them. But now that we have this notion of slope, we have a new way that we can plot points. And that's by plotting a point. So suppose I didn't already draw my graph. And I'm going to plot, go ahead, this point 0, 4. 1, 2, 3, 4. And my slope is negative 2 over 1. So I'm going to go down 2, right 1. So put a little tick mark so we know we're at 1. And then we'll go down 2, right 1. Put a point. And if you want, we could go down 2 more. Right 1 more to 3. We can connect those points. And so that's how we can plot a line with slope. Now let's go ahead and do one more example. So we have slope between half, a quarter, and 0, 2. Well, m is change in y over change in x. y2 minus y1 over x2 minus x1. So let's give these names. y2 is 2 minus y1 is a quarter over x2 is 0. So y2 minus y1 over x2 minus x1, 0 minus 1/2. And then we can go ahead and calculate that difference. Get a common denominator, we have 4 is our common denominator, so 4 times 2 is 8, minus 1 over 4 over negative 1/2. 8 minus 1 is 7/4 over negative 1/2. We can multiply the top and bottom by 2 over 1. That'll cancel to 1. This 2 and this 4 will cancel to a 2. We have negative 7/2. Negative 7/2. So m is negative 7/2. And now we can go ahead and see if, do we agree? Should our slope be negative? So here we have 0, 2, 0, 1, 2. And here we have a half, a quarter. So if that's 1, this is a half, That's 1, a half, a quarter, with something like that, left to right. It is negative, so we know that our sign's good, and we can be content with our negative 7 halves. So here we have point slope. Point slope, right? That was our y minus y1 equals m times x minus x1. It says, given a point and a slope, a point 0, 9, and slope m equals negative 2. Find the equation in point slope form. So find equation in point slope form. Actually, if you want, we can go ahead and start abbreviating this as point slope form. So given a point 0, 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I almost went high enough. 0, 9. And slope negative 2, so that means we go rise over run. We go down 2, right 1, down 2, right 1, down 2, right 1, 2, right 1, and so on, and we connect it. So this is the line for which we're finding the equation. Right, because if we look at one of these triangles, we go down to right 1. Our equation is point slope form is y minus y1, m x minus x1. So y minus y1, so x1, y1, y minus 9 equals m, or negative 2, x minus x1, x minus x1. And now that's just 0, so we have y minus 9 equals negative 2x. And that's as simple as that. And you know, we have to do a little bit more work if it hadn't given us the slope. So suppose we're given 2 points, negative 1, negative 3, and 6, negative 9. Let's go ahead and plot those 2 points, negative 1, negative 3, and 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. Connect those. That's our line of interest. And what we want to do is find our equation in point slope form. So we have a point, and well, we actually have 2 of them. And so we need our slope. M is change in y over change in x. So y2, negative 9 minus negative 3 over 6 minus negative 1. Negative 9 minus a minus is plus 3. Negative 6 over 6 plus 1 is 7. Our slope is negative 6/7. And so using our form, y equals y1, or y minus y1 equals mx minus x1, we have y equals, y minus y1, negative 3, equals m, negative 6/7, x minus, and since I picked this y value, I need to pick this x value, negative 1. Simplify that a little bit. Minus a minus is a plus. Y plus 3 equals negative 6/7. X minus minus is a plus 1. You're like, well, so you picked that point. Well, can I pick this point? And you absolutely can. In that case, it would look like y minus a negative 9 equals m, negative 6/7 doesn't change, x minus 6. Again, minus and minus, so y plus 9 equals negative 6 sevenths x minus 6. And so we have something that looks like that. And when we get to slope-intercept form, we can see why those are equivalent. So let's go ahead and rewrite this as slope-intercept form. So we have y plus 3 equals, distribute this, negative 6 sevenths x minus 6 sevenths. And then we're going to have to go ahead and subtract that 3 over. And here we have, I'm running out of room, so I'm going to write it up here. Y equals negative 6 sevenths x minus 21 plus 6 is 27 over 7. So we have minus 27 over 7. And then let's go ahead and look at this one here. What we end up having is, I'm going to bring it up here if that's okay. Y plus 9 equals negative 6 sevenths x plus 36 sevenths, right? Negative 6 times negative 6 is positive 36 sevenths. Subtract a 9 from both sides. Y equals negative 6 sevenths x, and I'm going to show my work for getting a common denominator. So 9 sevens are 63. So we have minus 63 sevenths plus 36 sevenths. So 63 minus 6 is 57, 47, 37, 27. So y equals negative 6 sevenths x minus 27 sevenths. And in both cases, we get the same number. So even though our point slope forms down here, y plus 3 equals negative 6 sevenths times x plus 1, and y plus 9 equals negative 6 sevenths x minus 6, look different when we convert them to slope-intercept form, our y equals mx plus a constant form, we end up getting the same value. And so since point slope form isn't unique, right? Like the same line can have a different form or equation depending on which of these reference points we use. We sometimes prefer to use our slope-intercept form because a line will have only one way to write its value. And so let's go ahead and work with slope-intercept a little bit. And if you want, you can call this slope-intercept form. Right, MB, so we have our point M form and our MB form. It's our slope-intercept, so it's is given a point, negative 1, 0, M equals 2 fifths, given a point and slope. We have y equals mx plus b. Let's go ahead and graph it. So we have x equals negative 1, y equals 0. Our slope is 2 fifths, so that means we go up to right 5. Up to 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5. At the very edge. Work backwards down to left 5. 1, 2, 3, 4, 5. And we can connect those, and we get something that looks like that. So to find our slope-intercept form, we have to substitute our slope. So we have y equals 2 fifths x plus b. But we know that at this point, negative 1, 0, our x and y values, make this equation true, because this is a solution. Remember, all of our points on our equation or our graph are solutions to our equation. And so we can substitute -1 in for x and 0 for y and see what we get. So here we have 0 equals 2/5. X is -1 plus b. 0 equals -2/5 plus b. And solving for b, b equals 2/5. So if we take our general form, our slope, and our intercept, and bring them together, we get y equals 2/5 x plus 2/5. You might be wondering, intercept. Remember, we talked about intercept as being the points where it hits the axes. So what is this intercept? Well, suppose, and let me use blue. So say let x equals 0. We have y equals 2/5 times 0 plus 2/5. We have y equals 2/5. So that means the point 0, 2/5 is on the line. So our point 0, 2/5 is on the line, and that's called our y-intercept. And so that's why we call this slope-intercept form, because it turns out that b is our y-intercept. So we have our point-slope form was our previous one, and then this one's called our slope-intercept form because this b term is always our y-intercept. And so we can go back here. Remember we had -27/7. Well, 3 7s are 21. And then we have 6 7s left, so almost 4. So if we go down 1, 2, 3, and this intercept is at almost 4. So that is at the point 0, -27/7. And so when we use our slope-intercept form, we know our slope and we know our y-intercept. And so we'll go ahead and look at one more example. But now we're going to be given 2 points, 4, -7, and 5, 3. So we have our m is change in y over change in x. We'll do 3 minus a -7, 3 minus -7 over 5 minus 4. 3 minus a minus is a plus. 3 plus 7 over 1 is 10 over 1. So m is 10. Y equals mx plus b. Y equals 10x plus b. And then we can pick either point. Because based on our work on the previous page where we were looking at slope-intercept, remember point-slope, or when we were looking at point-slope on the previous page, we showed that slope-intercept is unique. So pick either of these points, and I'll actually show you that both work out. We'll use this first one, so x and y, so -7 equals 10 times 4 plus b. And then our other one, so we have 3 equals 10 times 5 plus b. So here we have -7 equals 40 plus b. B is -47. And work out this one on the right. 3 equals 50 plus b. B equals -47. And so bringing those together, we know that m is 10. So y equals 10x minus 47. That also means when x is 0, y is negative 47, which is going to be somewhere way down here off the page. But we can plot our 2 points. X equals 4. 1, 2, 3, 4. Negative 7. 1, 2, 3, 4, 5, 6, 7 right there in my equation. And 5, 3. So we had 4, 5, 1, 2, 3. And so notice how with this 10, from left to right, it's really increasing. It's going up 10 and right 1. And so if we consider that back on this graph, so we had 1, 2, 3, that means 10 is something like nearly vertical. And so think about how as your number gets larger, it becomes steeper and steeper, or as it becomes a fraction, it becomes shorter, or less steep and less steep. So to bring some of these ideas together, and I'll just kind of give you a little summary of what we've talked about. Slope is a measure of steepness. We talked about how if slope is positive, from left to right, it'll go up. And if it's negative, from left to right, it'll go down. We have 2 forms for linear equations. We have point slope and slope intercept. So point slope, slope intercept. And the point can be any point on the line, and B is always our y-intercept. Point or slope intercept form is unique, and point slope is not. We can use slope to draw a point, or to draw an equation. So use slope to draw graph, rather, of an equation. And we need either 2 points, or if we have point slope, right here, 2 points, we can find slope. But if we have point slope or slope intercept, we have slope directly. And we showed that point slope and slope intercept really are the same forms. It's just using a special point, the y-intercept. And then what we have last is just kind of, and I didn't talk about this, but I want you to know that we can also think of slope is the rate of change of y with respect to x. That is the change in y. Remember we wrote that delta y for 1 unit change in x. And so that's just another way we can interpret slope. So for this homework, you'll be looking at working with points, point slope form, slope intercept form, either finding slope when you have 2 points, identifying the slope of a parallel or perpendicular line, or graphing given this method. Have a great day, everybody. I'll see you in the next video.